Okay, in this video we are going to continue the Euler-Cauchy differential equation, and when we have the case of imaginary roots or complex roots. Okay, so in general, I'm not going to start with one example. I'm going to start with a general case because I may not have enough space to write an example and the fix. Okay, so here's the general shape of the Euler-Cauchy differential equation, homogeneous, still homogeneous. So here is the characteristic equation that we saw in the previous videos, and here is the chicharronera to solve this quadratic equation. Now, you will have imaginary roots when this number is negative. When that happens, then you will have a square root of a negative number, which will become the I. So in general, the solutions will be the roots will be a real part plus minus an imaginary part, where alpha is going to be this number divided by 2a, and the beta is going to be this number here, but 4ac minus b minus a squared. Okay, now what to do when we have these cases? Okay, so the first solution, x1 is equal to is going to be x to the power of alpha plus beta I. So that is my first solution. So this is y1, and my second solution is going to be x to the power of alpha minus beta I. Okay, so my homogeneous solution is going to be the linear combination of them. It's going to be c1 x to the power of alpha plus beta I plus c2 x to the power of alpha minus beta I. Okay, that will be the solution, and that will be accepted for the mathematicians. But for engineering, the problem here is that we will have imaginary functions, and we want real functions. Alright? So how are we going to get an homogeneous real functions solutions? Okay, so we are going to apply again the Euler formula, but the Euler formula is something like this. The Euler formula is exponential of theta I equal to cosine of theta plus I sine of theta. Now, how can we apply this formula in here, because we don't have exponentials here. Okay, so we are going to apply in this way. Before doing so, let me tell you that the only difference between the first solution and the second solution is that here is positive and here is negative. Okay, so what I'm going to do is write my first solution as x to the power of alpha times x to the power of beta I. And my second solution is going to be x to the power of alpha times x to the power minus beta I. So you can see that this part is the same except for this. This is positive, this is negative. From where that comes from here, plus and minus. Okay, now the Euler formula for this kind of power. Okay, so what we are going to do is this. What I'm going to do is write x to the power of beta I equal to exponential of the natural log of x, and here beta I. Okay? So what will happen here? So is this the same as this? Yes, because this goes in the power and the exponential and the natural log cancels. So this is going to be exponential of beta, the natural log of x, I number. Alright? Now, if we apply that, if this is theta, then the Euler formula is going to be exponential of theta I is equal to the cosine of theta plus I sine of theta. Now, if it is negative, it's going to be cosine of theta minus I sine of theta. But in this case, what we are going to apply is that theta is equal to beta, the natural log of x. So we are going to apply it here. So if we apply that here, then it's going to be x to the power of alpha times x to the power of beta I. X to the power of beta I, I'm going to replace it by this exponential of beta, the natural log of x times I. And let me remark this. This is equal to this if you place this in the power and then the exponential and the natural log cancels. So s is going to be x to the power of beta I. But I'm going to leave it as exponential, because if I leave it as exponential, then I can use these two formulas. Okay, so x to the power of alpha times this x to the power of beta I is going to be the cosine of beta, the natural log of x. Is that the, if theta is equal to the beta, the natural log of x, plus I sine of beta, the natural log of x. And that's it. Alright. Let me remark this. This is just the formulas of the Euler formula. Okay. Now let's do the same for the other solution. So this is going to be equal to x to the power of alpha times. Now with this, when it is negative, the only difference is that this is going to be the same, except for the, here is going to be negative. So it's going to be the cosine of beta, the natural log of x, minus I sine of beta, the natural log of x. And that's it. Okay, I forgot that parenthesis there. Okay, now we still have a problem, because my first solution I just changed it from here to here, but I still have the imaginary number. And my second solution I still have the same problem. Okay, what we are going to do right now is make a first solution star with y1 plus y2. So what will happen if we make this plus this? Okay, on this side is going to be 2x to the power of alpha cosine of beta, the natural log of x. But this one, they cancel. Because they cancel, then this is my first derivative, my first solution star. Now, but what happens here is that this is still solution. Why is it still solution? Because it is a combination of two solutions. So if these two guys are solutions, then the combination of them is going to generate another solution. Now, the important thing, the precious thing here is that you don't have imaginary numbers. So I don't care about these two. What I care is about the function. Now, this is a real function. All right. Okay. So we get our first solution. Now, what about the other one? What we are going to do now, the second solution, star, I'm going to do y1 minus y2. So if we made the subtraction of this minus this, now the cosine is going to cancel. And here is going to be this minus this is going to be twice. So it's going to be 2i x to the power of alpha and then sine of beta, the natural log of x. And this is my second solution star. Okay. Now, this one is still imaginary function, but what we have done is we have taken the imaginary number in the coefficient. And what I'm going to take from here is just the real part, the real function. Alright? So I don't care again about this number, 2 or 2i. Why I don't care? Because in the end, if they are the solutions, then my homogeneous solution will be the linear combination of the two solutions, C1 and C2. Now, because they are constants, then what I care is about the functions, and this one is also real function. Now, here you have your formulas, okay? So, your formulas will be like this. Well, this is actually the formulas. Your first solution is going to be x to the power of alpha cosine of x, the natural log of, no, sorry. Here, cosine of beta, the natural log of x. And my second solution is going to be x to the power of alpha sine of beta, the natural log of x. Alright? Now, what is alpha and what is beta? Well, alpha is this number, and beta is this number. Okay, we have enough space, so let's do one example here. Let's do one example. Okay, let's do this example. Solve 4x squared second derivative plus 17y equal to 0. Okay, now it's a Euler-Cauchy differential equation because this is x squared second derivative. Now we don't have x and the first derivative. That's fine. So that means that b is equal to 0. So you don't have this part. b is equal to 0. Okay, but we do have the c, which is 17. Okay, let's build the characteristic equation. So it's going to be 4m squared, and follow this rule, b minus a, because b is equal to 0, so it's going to be minus 4. Minus 4m plus the value of c, 17, equal to 0. Okay, now because it is I'm sure it's going to be an imaginary roots. Let's use the chicharronera, because this 17 actually spoils everything. It's a very ugly number. Okay, so what I'm going to do is use the chicharronera, and 1 and 2 is going to be minus 4 minus 4, 4 plus minus the square root of 16 minus 4 times 4 times 17. Okay, divided by 2a, 2 times 4, okay, so it's going to be 4 plus minus the square root. Now, this 4 on 4 is 16, so if we factorize that 16, it's going to be 1 minus 17 over 8, okay, and 1 and 2 is going to be 4 divided by 8 is going to be 1 half, sorry, 1 half here, plus minus here. Now this is 1 minus 17, so that is going to be minus 16. So it's going to be the square root of 16 times 16 negative, which makes it an imaginary root. So it's going to be the square root of 16, 4, and the square root of 16, 4, but negative. So it's going to be here 16 divided by 8, so it's going to be 1 over 2 plus minus 16 over 8, I number. Now 16 divided by 8 is going to be just 2. Okay, so from here, what we get here is, this is my alpha and this is my beta. Okay, then my first solution will be, according to this formula, is going to be x to the power of alpha 1 over 2 cosine of beta, the beta is 2, the natural log of x. And my second solution is x to the power 1 half sine of 2, the natural log of x. Alright, now let's write the general solution, the homogeneous solution, sorry, because it is equal to 0, we only have homogeneous solution, so it's going to be C1 and C2, C1 times this solution, C2 times this solution. Now because we have this, we can factorize it, x to the power 1 half, and then C1 cosine of 2, the natural log of x, plus C2 sine of 2, the natural log of x. And that's it. So this is the solution when you have imaginary numbers. Okay, so with this video we have covered the 3 cases. The first case, remember, is a real different roots. We don't have problems there. On the second case, real repeated roots, and we already know how to find the second solution. And this is the case number 3, imaginary roots. And now you have here the formulas to find the first solution and the second solution, and that's it. Okay? Okay, so now next video we are going to cover the what to do when it is no longer homogeneous, when you have a q of x here. Now, we already have a method, and the method is parameter variation. See you in the next video.